Hi, and welcome to this video where I present our paper Sublinear Times Shortest Path in Expander Graphs that was accepted at MFCS 2024, the Mathematical Foundations of Computer Science. And this work is joined with Noga Lon from Princeton University, Allan Grønlund and Søren Fuglede Jørgensen at the company Quantify, and myself from Aarhus University. So what is the topic of this work? So what we look at is a very classic computer science problem, namely the shortest path problem, right? So you have two cities and you want to find the shortest path from first to the second. So for instance, I wanted to find my way from my workplace to the airport. Now, the input to this problem is naturally a graph of n vertices and m edges. You have a source S and a destination T. And the goal is to output a shortest path from S to T. In this talk, the graphs that we're going to be working with will be undirected graphs and unweighted graphs, right? So every edge has unit length and you can traverse the edge in both directions. Of course, I think you all know the classic solution to this problem is to run a breadth-first search, or BFS for short. And the idea is you just run the breadth-first search from the source. You keep growing layer by layer by layer until you visit the destination node, and then you found a shortest path from the source to the destination. So it would look something like this, right? We start growing, in some sense, a ball where you take all the nodes of vertices of distance 1, of distance 2, of distance 3, and so on, right? So you grow this ball around the source until finally this ball is large enough that you hit the destination node T. Okay. Of course, this algorithm, right, it's nice. It runs in linear time in the size of the graph, right? Even in the worst case, you only spend order m time if you use a Q in the right way. So it's a really efficient algorithm, and you know, there are instances where this is the best you can hope for. Okay. Now, what we want to try and look at in this talk is, could you say something about the average case complexity of this algorithm, right? So what does that even mean? And I'll try to explain. So maybe if we fix the source, right? So let's say I'm traveling from my workplace. Well, let's say in some average kind of sense, we say, okay, what if the destination is just uniform random amongst all the possible vertices of the graph? Does the breadth-first search actually run any faster than linear time? Can we say something about the running time of breadth-first search? And it's not too hard to convince yourself that at least the running time will be at least linear in expectation, linear in the number of vertices, maybe not the number of edges, but at least linear in the number of vertices, right? Okay, maybe for graphs with constant degree, this is linear in the full graph size. And so let me try to argue why this is the case. So one way to see this is to say, okay, take all the possible destinations, which means all the possible vertices of the graph, and try to order them by the time that this breadth-first search from the source would reach that node, right? So when this ball that is growing will reach the node. So here are some of the destinations that you could have tried to find a shortest path to. And we order them by distance from the source. And as you can see here in this picture, right, the closest of these vertices is closest to the source in this ordering. Second closest comes next, and so on, right? So we've ordered all these possible destinations by distance from the source. And now the argument is that if I pick the destination uniformly at random amongst all the destinations, its position along this ordering is uniform random, right? So there are n vertices in this ordering, and indeed, right, since this is also the order in which our algorithm will visit the vertices, when I'm searching for concrete destination T, I will have to have visited all the nodes or vertices that came before it in this ordering. So there are n possible destinations, and the ith one of them, if it's the ith one that is the destination, I will have to visit at least I vertices before I get to it. And since my destination choice was uniform random, I multiply each of these possible values of I by 1 over n. This sum is very well known, right? And if I divide it by n, I get n plus 1/2. Okay. So, and this is a lower bound, right? This is the actual number of vertices you expect to see before we get to T. And this was regardless of the choice of graph, right? So no matter what graph I take, if I fix a source, I run breadth-first search and pick a random destination, I will expect to visit a linear number of vertices before I get to the destination, right? So nothing better that we can hope for with breadth-first search. Okay. Now, what do people often do in practice? Now, so if I want to solve this breadth-first search problem, find the shortest path, at least a first simple heuristic that people use in practice, they also use way more advanced techniques, but a first step would be to do a so-called bidirectional breadth-first search. So this is some kind of heuristic to try and speed up the breadth-first search computation. So what is the idea? The idea is that you simultaneously grow a breadth-first search tree or ball, starting at both the source and the destination. So you kind of just grow them layer by layer by layer simultaneously. So take all the vertices of distance 1 from one of either the source or the destination, then all the vertices of distance 2 from either the source or the destination, and so forth. You grow these balls around the source and the destination, and you keep growing them until you find a vertex that is inside both of these balls, right? So if we draw a little bit more abstract picture here, I grow these balls centered at the source and the destination. Once they find a common vertex, I know that in the first ball that I grew, I have this breadth-first search tree, and I've now found the shortest path from T to V. V is this common vertex in the two balls. Similarly, right, in the ball I grew from S, I've also found the shortest SV path. And this is an undirected graph, right? So if I just stitch together these two paths, I will have found the shortest ST path. So I guess you can then ask now, okay, so this is heuristic, right? As such, there are no formal guarantees. It still has a linear in the number of edges, worst case running time. You can easily cook up examples where this is the case. But we know that just a single breadth-first search has linear time on average. Could you maybe hope to prove that somehow this bidirectional breadth-first search helps in some instances? And you can actually prove that it helps in some kinds of graphs, in particular, if I look at a random graph. Right, so this is not a fixed graph, but it's a family of graphs, if you will. So maybe let me just try to argue that this is the case. So what is a natural graph model is the Erdös-Rényi random graph. So an Erdös-Rényi random graph on n nodes is basically you have these n nodes initially. You look at every pair of vertices u, v, and then you say that the edge between them is present in this graph independently with some probability p. Typically, we think of p as being at least logarithmic in n, so that the graph is connected. Okay, so but this is basically the random graph model. Very simple model to consider. And now, if we were to try and prove that we have an algorithm that runs in less than linear time, and we somehow need to argue that the algorithm doesn't have to look at the entire input, and this means that we have to at least agree on some kind of access model in which this graph can be accessed. And what we're going to consider in this work is basically a query model where an algorithm can query with a node ID, a vertex ID, V, and then it is returned the adjacency list of this vertex. And here we assume that all the nodes of the graph just have integer IDs from, say, 1 to n. Right? So you just get the integer IDs of the neighbors of the vertex, and the vertex, the query operation is also just queried with the index of a vertex. Okay. So it's a very simple model. And in this model, right, maybe one could hope to do something in sublinear time. So let's try to get some intuition for why bidirectional breadth-first search might help in such a graph. Recall a single breadth-first search, we already argued in the beginning, right? If I just did one BFS, for every possible graph, the running time is linear, right? If it's at least a connected graph. Just by this random picking of the destination T, it would be it would take linear time before we visit it in this breadth-first search order. So even for random graphs, it would be surprising or great if bidirectional breadth-first search was better than linear. Okay, so let's try to examine what happens if I run bidirectional breadth-first search, and I run it until from both the source and the destination, and I run it until both of these balls that I'm growing contain square root n vertices. Right, so basically, I grow these balls until I reach the layer where I have square root n vertices in total inside these two balls. Okay. So let's try to look at what is the set of vertex IDs that fall inside the ball around the destination T. Well, if this is a random graph, right, the IDs of these vertices are just uniform random. It's a uniform random sized square root n size subset of vertex IDs. So the same goes for the ball around S. And this is not formally true, but it's almost true. These two sets of vertices are almost independently chosen. All right, so it's almost independently chosen sets of square root n vertices. It's not exactly true, but morally this is true. Right, so basically, yeah. So you just grow these balls, you get random IDs inside each of these balls. You have two sets now size square root n. So, right, by the birthday paradox, you will expect to see a common vertex in these two balls, right? Square root n times square root n, which is like a linear number of possible collisions, or basically you pick 2 times square root n elements out of a universe of size n, you will expect to see a collision, right? Good. So this is basically a property of bidirectional breadth first search, at least in random graphs. After just visiting around square root n vertices, you will have found the shortest path, so much less than linear time. Okay. And such different types of graph problems have also been studied in random graph models before. You'll often get something like close to square root n running time for shortest path and similar problems. Okay. So this is perhaps not extremely surprising, but still, it beats vanilla breadth first search. So there's actually a provable benefit to running bidirectional breadth first search. Okay. Now the question that we look at in this work is, are there other maybe more natural, what you can call a deterministic property of a graph, right? So you don't need to have a random graph model to say that bidirectional breadth first search actually beats linear time. This is some nice property that's perhaps well studied already in the literature that implies that bidirectional breadth first search is faster than linear time. Right. And the family of graphs that we look at in this work is so-called expander graphs, spectral expander graphs. So they're a very natural and well-studied family of graphs. And typically the ones that we're going to restrict ourselves to are so-called ND lambda graphs. So what are they? So they have n vertices. That's what n denotes. D means it's a d-regular graph. So all the degrees of all the vertices is d. Of course, this is a restriction, but it's just, the math and everything is just much cleaner if we look at this case. So this is, so an ND lambda graph is n vertices, all degrees of d. And what is this lambda now? So to understand the parameter lambda, we have to take this graph and then look at the corresponding adjacency matrix, right? So it's a matrix with a row and column per vertex and indicators 0 and 1, whether there's an edge between I and j, right? So very well studied object. So look at this adjacency matrix. What can we say about the adjacency matrix of an undirected graph? Well, first of all, since it's undirected, it's going to be symmetric. And of course, it's a real matrix, right? Just by definition, that's obvious. Furthermore, every row and every column has exactly d1s. This follows from the graph being d-regular. Okay. So this is what the matrix looks like. Now, so since the matrix is real and symmetric, we know that it has real eigenvalues. So we can order them. Lambda 1 is the largest eigenvalue. Lambda n is the smallest eigenvalue. Some of them may be negative, right? We don't know. It's not necessarily a positive semi-definite matrix. It's just a real symmetric matrix with real eigenvalues. And we can actually say a little bit more. In particular, we can try to look at what happens if I take the all one vector and multiply it onto this matrix. Then you can see that every row sum is d, and the d1s in every row. So I just get the all d vector, which is in fact a descaling of the all one vector, which means that the all one vector is an eigenvector of this matrix of eigenvalue d. Okay. And you could also show that d is the largest eigenvalue of this matrix, even if you take absolute values, d is the largest possible eigenvalue. This follows by every row sum and every column sum being bounded by d in absolute value. Okay, so lambda 1 is d, the largest eigenvalue is exactly d. All the others are smaller, at most d, in absolute value even. Okay, so these are just standard properties of such a graph. Okay, so now I can define what an ND lambda graph is. A graph is an ND lambda graph with n vertices, d regulars, all degrees of d. And it's an ND lambda graph if the largest of the second largest eigenvalue and the absolute value of the smallest eigenvalue, right? So this is the one that could be most negative if this is bounded by lambda, right? So basically I'm saying that the first eigenvalue, we know it's d. I have an ND lambda graph if all the other ones in absolute value are at most lambda. Okay, then the graph is an ND lambda graph. Okay, so what is known about, what are the possible ranges of this lambda? It is known that no matter what deregular graph you look at, lambda cannot be too small, right? There will always be one of these other eigenvalues that are fairly large. In particular, it will be at least 2 times the square root of d minus 1. And then minus little of 1 here. It's something like 1 over log n that you lose here. So it's basically, this is the smallest possible value of lambda. Right? Similarly, there's a family, graphs are called Ramanujan if indeed this lambda is basically 2 times the square root of d minus 1. And this is known that such graphs exist, right? So in some sense, graph is a good expander the smaller this lambda is, and the best you could hope for is what Ramanujan graphs satisfy 2 times the square root of the degree minus 1. It's the best you can hope for. Okay. So these are, this is like a family of graph, ND lambda graphs. So what we are interested in understanding is, if I run breadth first search in such a spectral expander graph, can we prove that it runs in sublinear time? And this kind of makes sense if you think about the property, the special property of expander graphs is that every time I grow a ball or around a set of vertices, or pick a set of vertices, most of the neighbors are outside. And also spectral expanders have, like, if you do a random walk in this graph, it's very uniform over the graph. It's very close to actually picking a uniform random vertex. Yeah. So in some sense, maybe you could hope that these balls that you grow around the source and the destination look a little bit like in the random graph model. Okay, so that's what we'll try to prove, that bidirectional breadth first search actually helps in expander graphs. Okay, so we have one key observation that we'll be using. This observation is not actually tied to expansion, but just for the graph to be deregular. So let's pick a source and destination, S and T, and let's look at some shortest path between them. Right, let's say the length of the shortest path is k. Now, if we grow these balls in bidirectional breadth first search, these two balls will meet after having expanded in a diameter of k half, right? That's exactly when they meet in the middle. Right? So I have to grow these two balls for k half steps, and then I'll have found this intersection, and I'll have found the shortest path. Okay. Now, you could ask how many vertices are inside these balls, right? How many vertices will I visit before I find this middle point? And as you can see, right, when you start growing the ball in the first round, the vertex has d neighbors. And in the second round, all the vertices basically have d minus 1 new neighbors, right? All the ones that do not lead back to where you came from. Of course, there may be overlaps, so this is an upper bound on the number of vertices in the ball, right? You go for k half steps. Each time you expand, the first time you expand by factor d, and otherwise by factor d minus 1 at most. So this is roughly d minus 1 to the k half, right? The diameter was k half. Okay. So we know now that we actually get a bound on the running time of bidirectional breadth first search if we have a bound on the diameter, right? If the diameter is k, then the number of vertices that we visit is d minus 1 to the k half. Okay. Now, of course, you can then, the natural question to ask is, okay, can we bound the diameter of an ND lambda graph, one of these expanders? And indeed, you can actually bound the diameter. It's a very old result from 1989 that shows the diameter of such an ND lambda graph is at most log base d over lambda of n, rounded up, but morally log base d over lambda of n. Okay, so now I guess we can ask, is this bound good enough to give us something non-trivial for bidirectional breadth first search? And maybe we should look at the best case scenario, you can see that this diameter shrinks. The smaller lambda is, right, this lambda, the smaller it is, the base of this log is larger, right, d over lambda. And we already said before that Ramanujan graphs have the smallest value of lambda, and that value is basically 2 times the square root of d minus 1. Okay, let's try to play with this and see what we get in the best case scenario for Ramanujan graphs. So, if lambda is basically 2 times square root of d minus 1, then d over lambda is basically, well, d divided by square root of d minus 1. It's almost square root of d minus 1. And then there was this factor 2, right? So it's something like a square root of d minus 1 divided by 2. Okay. So this is basically this ratio in the space of the log. Okay. So now we can insert this d minus 1 to the k half. If we insert, we can rewrite this d minus 1 to the k half. So the d minus 1 to the 1 half, right? That's basically the square root of d minus 1. Right? So it's square root of d minus 1 raised to the k. The square root of d minus 1, if I move the 2 to the other side, I get 2d over lambda. So that's what I put in here. So the number of vertices that visit is basically 2d over lambda to the k. And if you look at what is the diameter here, well, it's log base d over lambda of n. So even without this factor 2, even just the d over lambda to the k is linear. Right? So it's even worse, this number here. So we don't get anything useful from just this diameter bound, right? So frustrating. We cannot seem to argue that bidirectional breadth first search is sublinear time, even in these expander graphs. Okay. Now, maybe we can then try to relax it a little bit and try to look at the average case. Maybe most vertices T are much closer to the source than what the diameter says. Right? So in some sense, this would mean perhaps most of the graph is like a tightly concentrated component here where everything's close to each other. And then maybe there's a few branches which result in a large diameter, right? Maybe this is the case for these types of expanders. If indeed that's the case, then maybe most pairs of vertices will still be close, right? It could be possible. So let's try to argue this. Let's try to argue that most vertices will actually be close to the source, regardless of what source we pick. Right, so fix the source. We want to argue that most vertices are close to it. And this is basically a modification of Chung's proof, and it's very short. So to prove this, we're going to look at this adjacency matrix again and recall this fact about the eigenvalues, right? The largest one is D. All the other ones are bounded by lambda and absolute value. Okay. Now, a fact about adjacency matrices, I think maybe you've seen this if you've ever looked at all pairs shortest path. If I take an adjacency matrix and raise it to the kth power, then the value at entry I, j is the number of paths of length k from I to j. Right? So which is clearly true in the base case with case 1. It's basically is there an edge of length 1 between these two pairs of vertices. And in general, entry I, j gives the number of length k paths from I to j. Okay, so that's the first fact we need. The second fact is if I take a real symmetric matrix and raise it to the kth power, then what happens is that all the eigenvalues will be raised to the kth power as well. So the eigenvalues here are lambda 1 to the k, lambda 2 to the k, lambda n to the k. They might not be ordered in the same way as before, just because negative numbers might, if k is even, then maybe the negative numbers become larger than some of the positive numbers. But yeah, good. So these are the two facts that we need, two simple facts about matrices, adjacency matrices. And let's try to use this now. Okay, so let's say we are at the source S, and we want to bound the number of vertices of distance more than k from S. Right, let's say we have a set of them. There's set vertices of distance more than k from S. Let's try to bound set. Now, just by this first fact down here, if I look at the matrix A raised to the kth power, then in the row corresponding to the source S, all of these set vertices, the entry S, j has to be 0, right? Because there's no path of length k from S to this vertex j, just by a definition of these vertices having distance more than k. So we have a bunch of entries in this A to the k in row S that are all 0. Okay. Now, what we're going to do is we're going to form basically an indicator vector for this set of vertices. It's a vector that has an entry for every vertex. It has a 1 for those j's where we have a 0 in this row, and it's 0 elsewhere. So just an indicator for the set of vertices of distance more than k from the source. Okay. And okay, so the first observation is if I take this indicator vector and multiply it with a to the k, then I'm summing the rows or the columns corresponding to this set. And just by definition, all of these columns have a 0 in the S row, the row corresponding to S, right? So the sum here, a to the k times the indicator, has a 0 in position S. So if I multiply it by the standard unit vector corresponding to row S on the left here, I get a 0, yeah, just by definition. Okay. So this is simple observations, and let's now try to use this to bound set. Okay. First, what we're going to do is we're going to rewrite this indicator vector e to the set. And this is basically just using what you'd say a Gram-Smith step, because basically we write it as some scaling of the all ones vector. Right? So if you work out the math, the scaling will be set over n times the all ones vector, plus some scaling of a vector v that is unit length and orthogonal to the all ones vector. So this is just a Gram-Smith step. So the all ones vector is going to be orthogonal to this v, and also the scaling onto this v vector, the beta, it will always be at most the norm of the original vector here. It's going to be less because of this set over n, but it's definitely at most the norm of this vector, this indicator vector. This indicator vector has set once, so the norm of this one is square root of set. Okay, so it's just a simple rewriting of this indicator vector. Okay, so let's see that this is useful, and now we have all the ingredients. So we had from up here that 0 is equal to this product here, a to the k times the indicator for the set of vertices that are further away than k, times this inner product with this standard unit vector corresponding to S. Now I insert the rewriting of the indicator for the set here. So I just plug it in. And then we use linearity, and we get one term here that is the set over n, the indicator for, the standard unit vector for row S times a to the k times the all ones vector. And then we have this beta factor, a to the k times the v vector times this indicator for row S. Okay, so it's just by linearity. Now we're going to use that this all ones vector is an eigenvector for the matrix A. In particular, it's also an eigenvector for the matrix A to the k, corresponding to the largest eigenvalue. Now the largest eigenvalue is not d anymore, but it's d raised to the kth power, right? This was by the second fact. So which means that when I take 1 and multiply it with a to the k, I just get a bigger scaling of the all ones vector, namely the d to the k scaling of the all ones vector. Right, so that's all that happened here. I just used that the all ones is the largest eigenvector. All right, so basically here, the second observation that we use in the first part here is that d to the k is just a constant factor. It moves in front here. And then we have the inner product between the indicator vector for the row S and the all ones vector. That inner product is just a 1. Right, so that's what we have here. And the second part here, now we want to say that we want to show that this value is large. Okay, so how big is this number? Well, it can be a negative number, but the magnitude of the number by Cauchy-Schwarz, the inner product between any two vectors, is at most the product of the norms of the vectors. Right? So this is what we're using here. Beta, also we had a bound on this. It's at most square root of set. Also in absolute values, or maybe I should have written absolute value of beta is at most square root of set. But this is at most the square root of set, the norm of this indicator, this standard unit vector, and the norm of a to the k times v. Okay. Now, the norm of the standard unit vector is just 1. That's great. And now we have to bound the norm of a to the k times v. And here the observation is we're using that v is orthogonal to the all ones vector, which means that v lies in the span of all the eigenvectors mu2 to mu_n, corresponding to the eigenvalues lambda 2 to lambda n. In a to the k, these have been raised to the kth power, but just by definition of a lambda nd lambda graph, all of these eigenvalues were bounded by lambda and absolute value, which means that in the a to the k matrix, it's bounded by lambda to the k. Right, so we now have this lower bound here, or this inequality, that 0 is less than or equal to z or n times d to the k minus root z lambda to the k. So we just wrote it up here. This is this fact that we established. And if you rearrange terms, put the z's on one side, right? So you divide by root z, you move all the other terms to the other side and you square it. You get this inequality that the number of vertices of distance smaller than k, the set, is at most n squared times lambda over d to the 2k. Okay, is this bound useful? Let's have a look. If we insert a value of k that's at least 1/2, so that cancels the 2, log base d over lambda of n over delta, then the number of such vertices is at most delta n, right? So we can make a small fraction of n, or we can make it much, much smaller. So if I insert such a value of k, I have at most delta n vertices that are further away. Okay, and if we compare this to Chung's bound on the diameter that we used before that didn't bias anything, basically what we gain is this factor 2 on k here, right? Before there are few vertices that are far away. So if we try to insert this in the bounds that we had on the number of vertices visited by bidirectional breadth first search from S to T, so we can try to plug in the value of delta, and then we want to say, okay, the bidirectional breadth first search from S to T visits at most d minus 1 to the k half vertices if the distance between them is k. With 1 minus delta fraction of all the t's, we can insert a value of k, the distance of at most a half log base d over lambda of n over delta. Right, so we insert this in place of k. Well, then we get d minus 1 to the 1/4 log base d over lambda n over delta. Okay, and I guess before we saw with the Ramanujan graphs, it was convenient to have a square root of d minus 1 down here. So I could also just kind of move a square root down, and then it's just a half log base d over lambda to the n over delta. Okay, so this is some bound now on the number of vertices and nodes that we visit. Okay, and let's look at the best case scenario when our graph is a Ramanujan graph. This is the case when this base here, the d over lambda, as we argued before, is basically square root of d minus 1 divided by 2. So it's almost like the square root of d minus 1 to the log base square root of d minus 1 of something. So this simplifies, and we can just insert, if we insert this value square root of d minus 1/2 into this bound, we can rearrange the terms a little bit, and basically what we get is, well, we have one term, if you just plug in the square root of d minus 1, so the square root of d minus 1 to the 1/2 log base square root of d minus 1 over n over delta, you get this square root n over delta term, and then we have another third term over here. But basically we get down to around square root n vertices that we have to visit instead of a linear number of vertices, right? So that's the benefit. We have this third term over here that says we're going to visit a little bit more. If we look at the magnitude of this expression, see that the base, it's 2 raised to some number where the base is increasing with this degree d. So basically what we can see is that for large enough constant degree, basically we can make this whole expression n over delta to the 1/2 plus some epsilon of d, some small constant that goes down with d. Okay, so this is basically what we get here for the Ramanujan graphs. So something close to square root of n. If I do bidirectional breadth first search from S and T, for most values of t, I only have to visit around square root n vertices in this bidirectional breadth first search. So this is the conclusion that we get for bidirectional breadth first search and expander graphs. So you have to visit around square root n vertices in this bidirectional breadth first search in the best case scenario for Ramanujan graphs, and we also get bounds for other graphs. In the paper, we also show some other results. In particular, maybe one could ask, is it just our analysis that is not tight based on the diameter? Maybe every graph, if you run bidirectional breadth first search, you'll actually find a common vertex quicker than the bound that we got from the diameter. But we have given an example of an expander where you actually have to visit into the 0.999 vertices and nodes before you're done. So this is basically tight. You cannot hope to show that bidirectional breadth first search for every pair of vertices is efficient. Motivated by that, we also look at a short path algorithm. basically say for every ST path, we don't want to find the shortest path, we want to find a short path between them, right? We can actually find a path that's within a constant factor of this log base d over lambda of n with high probability. The algorithm is really simple. We do breadth first search from the source until we've seen around root n nodes. And then we run a number of random walks starting at the destination t, all of length order log base d over lambda of n. We run around root n of these random walks. And because of random walks and nearly uniform random in the vertices that you visit are almost uniform random, in expander graphs, there's a big chance that one of these paths will hit the BFS ball that you grew from the source, and you'll have found a short path. Right, so that's the idea here. So with high probability, these will intersect, and also the breadth first search ball that you're growing around S is also small in diameter. Okay. Finally, the paper also has lower bounds showing that maybe you could think maybe there are other algorithms in bidirectional breadth first search that are even better. Maybe you can beat square root n by doing something more clever. Maybe you sample a bunch of vertices at random in the graph, grow some balls and something, right? What have you. But in the paper, we also show lower bounds for all algorithms, sublinear time algorithms, not just bidirectional breadth first search. And we show that in such expanders, they have to query around square root n nodes, right? So basically, bidirectional breadth first search is nearly an optimal strategy. Good. This is, if you want the technical details of the paper, this is the hardest technical part of the paper and the main contribution here. But I decided to present this cleaner algorithm in this talk. Yeah, so that's it. Thanks a lot for listening.